classification metrics. We just learned that after our machine learning process is complete, we use performance metrics to evaluate how well our model did. Remember, in that train test split step, we ended up running our trained model on some test data and then evaluating its performance. In this lecture, we're actually going to discuss in more detail how we actually evaluate the performance of a model. And that comes in discussion with classification metrics. The key classification metrics we need to understand are accuracy, recall, precision, and F1 score, which is essentially a combination of recall and precision. But first, we should really understand the reasoning behind these metrics and how they actually work in the real world. So we're going to follow along a little bit in a process with some more realistic example, such as classifying a spam versus ham message. So typically, in any classification task, your model can only achieve two results. Either your model was correct in its prediction, or your model was incorrect in its prediction. And fortunately, incorrect versus correct, that expands to situations where you have multiple classes. It doesn't matter if you're trying to predict categories with 8 different types of classes or 8 different types of categories. Your model fundamentally only has two outputs, either a correct output or an incorrect output when it comes to classification. Now, for the purposes of explaining the metrics, we're going to imagine a binary classification situation where we only have two available classes, spam versus ham. In our example, we're going to be attempting to predict if a text message is spam or ham, ham being another word for a legitimate message. Since this is a supervised learning process, we were going to first fit or train a model on training data. Then we will test the model on testing data. Once we have the model's predictions from the X test data, we compare it to the true Y values, that is the correct labels. Because remember, in a supervised learning process, we're dealing with historical information that we already have the labels for. Keep in mind, there are a few steps to convert the raw text message information into a format that the machine learning model can understand. So whenever we're dealing with raw text, we're going to have to do a little bit of work in vectorization in order to translate the raw text into numerical information that the machine learning model can understand. So whether it's a text message from a cell phone, whether it's an email, whether it's a movie review that's been written down, there will be some steps that we're going to cover later on in actually converting that raw text information into numerical information. We're going to discuss these methods in much more detail later on. So just to give you a brief overview of kind of the process of vectorization, we're going to wave our hands a little bit here, but essentially what we're doing is we're taking some sort of raw text message from the testing data set, that is the X test that we saw in the previous lecture. We pass it through some vectorizer, and then we have a vectorized version of that. So to give you just a brief idea of what that actually is, or what that would look like, essentially, we would have some raw text information. So here's a text message from a cell phone saying, "Hey, how are you doing? I've been doing well," etc. Theoretically, after we pass it through the vectorizer, it should be formatted in some sort of vectorized format that is a numerical matrix that the machine learning model can then understand. You can imagine that we can do things such as count the number of times certain words show up, and that would be numerical information, and we would format it in a way that the machine learning model can understand. We're going to learn about this entire process in a lot more detail. Things like term frequency, inverse document frequency, bag of words, those are all different processes that we can employ in order to vectorize text information. But we're going to learn about that in the feature or text feature extraction lecture. But for right now, we can kind of imagine behind the scenes there's some sort of vectorization process taking place. So we set up this vectorization in a pipeline, and again, there's many ways of transforming that raw text into numerical information. For right now, since we want to focus on understanding classification metrics, we're just going to assume that there was some underlying vectorization process that took place. Okay, so let's actually jump right into the middle of that machine learning process pipeline that we saw in the previous lecture and assume that we have a trained model, and the model was trained on the training data. So we took in our X train and our Y train, and then we trained the model. Now it comes time to actually evaluate the model's performance. So what we need to do is take in our test data set and then pass it into the trained model. So for example, I go ahead and grab a test message from X test. And if you're wondering what X test means, go ahead and watch the previous lecture. We explained it there. So we have this text message from a cell phone, and it's from the X test data set. and we pass it into the trained model. Now remember, because this is a test message and this is supervised learning with historical labeled information, we actually already know whether or not this is a ham or spam. So keep in mind, we always already know the correct label for this particular test data point. That's going to allow us to actually compare the output of the trained model, whether it's correct or incorrect. So we pass it through a trained model, and let's say in this particular instance, the trained model said, I think this text message is ham, or it's a legitimate test message. Then what we do is we simply compare the correct label that we already know to be true against the prediction that the trained model output. So here we say, was ham equal to ham? And in this case, it's correct. So here we get a correct prediction. Keep in mind that for other data points, the trained model could be incorrect. It might say, oh, I think this text message is spam. And in that case, it would be an incorrect prediction. So what we're going to do is we just repeat this process for all the text messages inside of our test data. At the end, we're going to have a count of correct matches and a count of incorrect matches. Here's the absolute key realization and probably the most fundamental part of this particular lecture. In real-world situations, not all incorrect or correct matches hold equal value, which is why we actually have those various classification metrics. It's not enough to understand that you got a particular count of correct versus a particular count of incorrect. It's various ratios that we need to take into account. So in the real world, a single metric won't tell the complete story. So to understand all of this, we're going to bring back those 4 metrics we mentioned at the beginning and see how they're actually calculated. And we could actually organize our predicted values compared to the real values in what's known as a confusion matrix. And in the next lecture, we're going to have a whole discussion of the confusion matrix. But for right now, let's look at accuracy. Accuracy in classification problems is the number of correct predictions made by the model divided by the total number of predictions. So again, what we do is we count up or tally up how many times the model was correct, and then we divide it by the total number of predictions the model made. For example, if the test dataset was 100 messages and our model correctly predicted 80 of those messages from the test dataset, then we would have 80 out of a total of 100 predictions that were done correctly. And that means we were 0.8 or 80% accurate. Accuracy is really useful when target classes are well balanced. So in that example, it would mean that we have roughly the same amount of spam messages in our test data as we have ham or legitimate messages. Now, here's a problem. Accuracy is not a good choice with unbalanced classes. Let's imagine a situation where we had 99 legitimate ham messages and 1 spam text message. If our model was a simple line of code that always predicted ham, that means we would get 99% accuracy, even though it was incorrect on every single instance of spam. We got unlucky because we had an unbalanced class situation in our test dataset. So in this situation, we're going to want to understand recall and precision. That's going to give us a better understanding of how it performs on the other smaller class. So let's quickly go over some formal definitions of precision, recall, and F1 score. F1 score is simply a combination of precision and recall. We're going to go over their formal definitions, and I think usually they make a lot more sense when you see them in combination with the confusion matrix. So keep in mind, in the next lecture, you'll see a confusion matrix which should clear up precision, recall, and F1 score with further detail. Let's start with recall. Recall is the ability of a machine learning model to find all the relevant cases within a data set. And the actual mathematical formula for definition of recall is going to be the number of true positives divided by the number of true positives plus the number of false negatives. And when we see this in combination with the confusion matrix, it'll make a lot more sense. So keep in mind, in the next lecture, we're actually going to see the formulas and how they're calculated. So don't worry too much about these formal definitions. Precision is the ability of a classification model to identify only the relevant data points. Precision is defined as the number of true positives divided by the number of true positives plus the number of false positives. And in the next lecture, we'll talk more about true positives, true negatives, and false negatives. So keep in mind, often you have a trade-off between recall and precision. While recall expresses the ability to find all relevant instances in a dataset. Precision expresses the proportion of the data points our model says was relevant that actually were relevant. And in cases where we want to find an optimal blend of precision and recall, we can combine the two metrics using what is called the F1 score. The F1 score is the harmonic mean of precision and recall, taking both metrics into account in the following equation. We say F1 score is equal to 2 times, and in the numerator we have precision times recall, and then in the denominator we have precision plus recall. And this is known as taking a harmonic mean instead of just a normal mean. And the reason we use the harmonic mean instead of a simple average is because it punishes extreme values. Let's imagine we had a classifier with a precision of 1.0, but a horrible recall of 0.0. If we were to perform the normal mean, we would end up getting an F1 score of 0.5. So that's just a simple average. If we take the harmonic mean, we can be a little smarter about it and really punish this model for having a horrible recall. Because we're going to say precision times recall, then that's going to say 1 times 0 is 0. So it means the F1 score automatically becomes very small, or 0, if one of these values, either precision or recall, happens to be very poor. So again, it's a better display of the optimal blend than just a simple average, because it's punishing extreme values. So precision and recall, as I keep mentioning, typically make more sense in the context of a confusion matrix. So in this next lecture coming up, we're going to explore this confusion matrix and again talk again in more detail about the different classification metrics we'll be using throughout this section of the course. We'll see you at the next lecture.